Hello, welcome to the online course on pericyclic reactions and organic photochemistry. We are in the 6th week in module 26, for example, and this is a tutorial session. This is tutorial session number 4. In this tutorial, we will consider a variety of problems pertaining to pericyclic reactions, from cycloaddition to sigmatropic rearrangement to Yin reaction and so on. This is important because this exercise will help you to identify certain problems in the pericyclic category. Now the first problem is stated like this. Two successive pericyclic reactions are involved in the following transformation. Identify the pericyclic steps. In other words, this molecule is undergoing thermal decomposition to generate carbon monoxide, benzene and anthracene. Now this particular molecule, if you look at, this is essentially a Diels-Alder addition product of this dienone, bridged head dienone, the bridged ketone, which is a dienone, undergoing a Diels-Alder reaction with the anthracene 9-10 position. In other words, anthracene undergoes Diels-Alder reaction as well as retro Diels-Alder reaction at the 9 and 10 position. This is the 9th position and this is the 10th position of anthracene. Now CO is probably formed from a chelotropic reaction of a bicyclohepta 2,5-dienone, which is a dienone which is coming from this particular moiety, which is formed in the retro Diels-Alder step. So one can consider the reaction as initially a retro Diels-Alder reaction as indicated by these 3 small arrows that are shown in this structure, which results in the formation of anthracene and this unstable 2,2,1 bicyclic ketone. The 2,2,1 bicyclic ketone under the reaction condition will not survive. It readily undergoes the loss of carbon monoxide with the formation of benzene, which is aromatic product. So essentially this reaction, this particular molecule undergoes initially a retro Diels-Alder reaction followed by a chelotropic elimination of carbon monoxide in the formation of benzene and anthracene, for example, in this reaction. It is a very interesting reaction because a reactive intermediate like this one is stabilized in the form of a Diels-Alder adduct in this particular instance. In fact, the forward reaction would be difficult to do because this is not a readily available starting material. So this molecule would have been prepared by a different route other than a Diels-Alder reaction route in this particular case. Now the second problem deals with again a cycloaddition reaction of higher order. Identify the product of the higher order cycloaddition reaction in the following reaction. In other words, dimethyl acido-dicarboxylate, which is acting as the enophile, dienophile for example, and this is acting as a polyene which is undergoing a higher order cycloaddition reaction. The higher order cycloaddition reaction is a 8-pi 2-pi cycloaddition reaction as indicated on the arrow. It essentially takes place at room temperature around 20 degrees Celsius. If you look at this molecule, this is hexamethylene, bis-hexamethylene cycloheptadiene. It can undergo a cycloaddition process across this methylene and this methylene. In other words, this would be a 8-pi cyclic 8-pi system which is undergoing the cycloaddition reaction. This is the 2-pi component which is undergoing the cycloaddition reaction. So essentially the cycloaddition product would arise from the addition of this carbon onto the nitrogen and this nitrogen onto this carbon with the concomitant rearrangement of the pi system in the cyclic system. So that would result in the formation of this particular molecule. You can see here the N double bond N has become a N single bond N because of the cycloaddition process, and these two methylene groups are essentially appearing in these two positions which are connected to the nitrogen, and this methylene here, which is the sp3 methylene, is essentially acting as the bridge in this particular system. So this is the product of 8-pi 2-pi cycloaddition reaction. Since the reaction is given in a straightforward manner as a 8-pi 2-pi cycloaddition reaction, one can easily figure out the answer for this particular question. If this information is missing, it could be a misleading question because one can think of a Diels-Alder reaction and so on with this molecule. This molecule has a periselectivity in that it undergoes only an 8-pi 2-pi cycloaddition reaction, not a 4-pi 2-pi cycloaddition reaction, as it is also possible in this particular case. Again, another example of a higher order cycloaddition reaction. Identify the intermediate formed in the following reaction. Identify the process involved and the Woodward-Hoffmann rule for this particular process. What has happened is an hexamethylene cyclohexatriene is undergoing a cycloaddition reaction with dimethyl acetylene dicarboxylate, essentially at low temperatures in the freezer although it is a very slow reaction, it takes 3 days for this reaction to proceed, gives an intermediate. The intermediate on treatment with palladium and charcoal has gone to an aromatic compound which is an azulene derivative. This 7-membered 5-membered fusion is an azulene ring, so it's a dimethyl dicarboxylate ester of the azulene derivative is what is formed in this particular case. So one can think of a cycloaddition process to take place between carbon number 1 and 3 and carbon number 1 and 2 of the acetylene. In other words, this carbon and this carbon can undergo cycloaddition process because you need to form a 5-membered ring fusion. So this will be 1, 2, 3, 4, 5. So 5-membered ring can be formed by this combination of 1, 2, 3 and this 4 and 5 coming from the acetylene unit. So the cycloaddition process is mentioned here. It's essentially this is acting as an 8 pi electron system because of the rearrangement of the pi system completely to give a conjugated triene unit here. So it's a 8 pi 2 pi cycloaddition reaction. It is a 4n plus 2 combination. So it is suprafacial. Suprafacial is allowed process according to the Woodward-Hoffman rule. It is very similar to Diels-Alder reaction, which is also a 4n plus 2 cycloaddition reaction. It's a suprafacial cycloaddition reaction. The product that is formed is not aromatic because this is not a fully conjugated. This is aromatic because it is a 10 aniline system. This is 6 plus 4, 10, and it is azulene as a mighty. Azulene is a very well known aromatic compound, whereas this is a dihydroaromatic compound because this is an sp3 carbon here and this is also an sp3 carbon. The palladium and charcoal is known to do dehydrogenation of dihydroaromatic compounds to aromatic compounds. So the second step is involved in this, that is involved in the process, is the dehydrogenation process. The dehydrogenation of the dihydroazulene using palladium and charcoal to give azulene derivative is the final step for this particular reaction. It's a very interesting reaction because this is one of the synthetic methodologies to make azulene derivatives specifically substituted in this position, or if it is specifically substituted on these positions also, one can think of alternatively the substituted cycloheptatriene, hexamethylene cycloheptatriene as a starting material to prepare azulene as the molecule. So one can take it as a synthetic methodology to make azulene derivatives of this type by higher order cycloaddition reaction. Here is another interesting question. Account for the formation of product A, which is formed at room temperature when this diphenyl butadiene reacts with acrylic acid. However, this on heating, A on heating undergoes isomerization. You can see here one of the center is different stereochemistry. This is all cis stereochemistry, whereas this is 1,4 cis and 1,2 trans kind of a stereochemistry. This is a diastereoisomer of this particular molecule. So how is it formed? Initially one can think of a Diels-Alder reaction between these two molecules. As you know, Diels-Alder reaction is highly endoselective, especially at low temperature, because this is a kinetic product. The endo product is kinetic product because of the secondary orbital interaction that can take place. So one can now think about a endoselective Diels-Alder reaction. You can imagine this hydrogen in this position containing the phenyl group and this hydrogen in this position and the hydrogen in the olefin where X is the substituent COOH. They all point in the same direction in the transition state. So the product that is formed would have the phenyl groups and the X group pointing in the same direction backward. So one can see the phenyl COOH and the other phenyl, they are all cis with respect to each other, and these three hydrogens are also cis with respect to each other. This is the formation of A. In other words, this particular product is same as this product in terms of the stereochemistry, relative stereochemistry of the three centers that are generated in this particular molecule. Now, how is it that this is undergoing isomerization to give this particular product at high temperature? Now, please recall that Diels-Alder reaction is a reversible reaction at high temperature. In other words, the retro Diels-Alder reaction can take place, and at high temperatures, in fact, the Diels-Alder reaction prefers XO approach, which is a thermodynamically favored approach. The endo approach is kinetically favored because the transition state is stabilized by secondary orbital interaction, so it has a lower activation barrier, whereas the XO with the X functional group outward pointing outward of the pi system is thermodynamically more stable because this is sterically hindered approach of the diene and the dienophile. So initially at room temperature, for example, the endo approach takes place and the endo product is what is formed in this case. This is a kinetic product. Sorry, there is a mistake here. This should be the kinetic product that is formed in this reaction. However, this reaction is a reversible reaction. At 100 degrees, of course, the initially formed adduct can undergo retro-Diels-Alder process to give the starting material. This can now approach in an exo manner. The endo approach gives this product. This should be product A, is not product B. There is a mistake that I want to point out. It should be B. It should be A here because this is all cis. This is also all cis. Now the exo approach would put the 2 hydrogen outward and this hydrogen inward. So the 2 hydrogens in the 1,4 positions are cis with respect to each other, whereas the hydrogen containing the carbon bearing the COOH group is trans to this particular hydrogen. So you can see here this hydrogen is pointing in the front, which is not shown of course in the structure. This hydrogen is pointing inward, so those 2 hydrogens should be trans with respect to each other. So this is the product B, where you have 1,4 cis and 1,2 trans, which is a thermodynamic product in this particular case. So this problem illustrates 2 possibilities of Diels-Alder reaction. The first possibility is the endo approach at low temperature, and of course at high temperatures the Diels-Alder reaction can be reversible. Once it is reversible at high temperature, Diels-Alder reaction can be exo approach possibility. So exo approach gives a thermodynamically stable product, whereas the endo approach gives the kinetic product. That is the message you get from this particular problem. Here are some interesting molecules which needs to be synthesized by cycloaddition reaction. The question is, what cycloaddition reaction would you use for the synthesis of the following compound? If you take this compound, this is a cage structure and this is also a cage type of a structure. And what is interesting feature in this molecule is this 4-membered ring. As we all know, the 4-membered ring can be formed by a 2+2 cycloaddition reaction. So if you I will give the example of this molecule for the synthesis. You figure it out yourself what is the starting material for this particular molecule. I am not going to solve this problem because once I solve this problem, an equivalent synthetic approach should be possible for this molecule. The only clue I can give here is this carbon and this carbon bearing the 2 esters come from acetylene dicarboxylic acid. In other words, dimethyl acetylene dicarboxylic acid is one of the reactants for this particular molecule. Take the clue and do it yourself to solve the structure of this, to solve the synthesis of this particular problem. I will deal with this problem. Let us to start with. The first molecule has 4-membered ring, which can be formed by a photochemical 2,2 cycloaddition reaction. The 4-membered ring is shown very clearly in the red color, and the 2+2 proposed 2+2 cycloaddition reaction is shown here. In other words, this molecule, when it undergoes a 2+2 cycloaddition reaction, would give this molecule. This is a retrosynthetic arrow. We are doing a retrosynthetic analysis by putting the double bond here. In fact, the reverse reaction is what one would perform to do the 2+2 cycloaddition reaction. Now this is a product which is essentially a Diels-Alder product of cyclohexadiene 1,3-diene and benzoquinone in an endo approach. So you can see here this methylene bridge here, CH2CH2 bridge, is essentially coming from the CH2CH2 of the cyclohexadiene undergoing a Diels-Alder reaction. So this 6 carbon fragment is essentially coming from the dienone fragment is coming from the benzoquinone moiety as the dienophile. As you know, benzoquinone is a powerful dienophile. It will readily undergo Diels-Alder reaction with hexadiene. So the initial reaction is the endo approach reaction. Essentially this reaction can be performed at room temperature. It doesn't need any heating because of the high reactivity of the benzoquinone as the dienophile. So you can see here this methylene bridge is shown in blue color, so that is resulting in the structure, the blue color that is shown here. And this the olefin that is formed here and the olefin that is residual olefin, which does not react under the Diels-Alder condition, are ending up in this close proximity with respect to each other. Now because of the endo approach and the close proximity, this is the endo substituent for this 2,2,2 bicyclic system that would put this double bond and this double bond in close proximity, and that is what results in the 2,2,2 photochemical cycloaddition reaction. So a Diels-Alder reaction between hexadiene and benzoquinone would give you the precursor, which puts the 2 double bond in close proximity in the endo approach, and this molecule is the precursor for that final target molecule, which can be obtained by a photochemical 2 cycloaddition reaction. So this is a thermal 4,2 suprafacial cycloaddition. This is a photochemical 2,2 which is also a suprafacial cycloaddition process. So the 2 cycloaddition process would result in the synthesis of this compound. You can also imagine the same kind of a strategy for this. Already clue is given that dimethyl acetylene dicarboxylic acid is 1 unit, and imagine that this 4-membered ring is going to be formed by a 2,2 cycloaddition process of a precursor, suitably substituted precursor for synthesizing this molecule. So solve this problem yourself so that it gives you some exercise to do in terms of identifying the process involved and the starting materials involved in the synthesis. Now here is a question: when this tetraene and the dimethylacetylene dicarboxylic acid are heated together at 200 degrees Celsius, the product formed are dimethyl phthalate and butadiene, which is dimethyl substituted butadiene. There are 5 pericyclic steps involved. This is a clue that is given in this solving this problem. So one has to find out what kind of a connectivity exists in the final product which arises from the fragments of this particular molecule. You can clearly tell that this diester and these two carbons, the ortho carbons and the diester, should come from the dimethylacetylene dicarboxylic acid. So I have written the dimethylacetylene dicarboxylic acid in blue, and this blue fragment in the product, which is this particular product, should essentially come from the dimethylacetylene dicarboxylate. Now the red portion, which is the diene portion in this molecule, essentially should come from the diene of this particular molecule. So the red portion here should correspond to the red portion here, and this black portion, which is the diene portion, essentially should come from this olefin and this olefin. Somehow the connectivity should be made here between them. Finally, the two methyl groups should essentially come from the two methyl groups which are in the starting material. So which is, there are 2 or 3 things which you can say unambiguously. The methyl groups are present in the final product as well as in the starting material. So this methyl and this methyl should come from essentially these two positions, should result in the formation of this, and the 2 ester group and this connecting carbons should also come from the dimethylacetylene dicarboxylic acid. That much one can say for sure in this molecule. Now when you take a tetraene like this, it has a propensity to undergo the electrocyclic ring closed set reaction. This is written in the transoid conformation. If you write it in the cis-oid conformation, which is this molecule, these two are equivalent molecule, identical molecule. You can see here there is a trans double bond, cis double bond, cis double bond, and a trans double bond. So you start from trans, cis and trans. This is the same molecule as the one that is shown here. The reason it is written in the cis-oid conformation is so that you can do the electrocyclic ring closing process across carbon number 1 and carbon number 8 of this octatetraene. So the octatetraene undergoes the electrocyclic ring closing reaction, which is a thermal reaction at 220 degrees Celsius. It should be a 4n electron system. It's a 8 electron system, and it should be a conrotatory process. The conrotatory ring closer across carbon number 1 and 8 will essentially put these two methyl groups trans with respect to each other. So one gets a trans dimethyl substituted cyclooctatriene molecule, and this does not stay put like this. It further undergoes electrocyclic reaction. This is something we have seen during the course of the electrocyclic reaction that we studied in the earlier modules. So this is behaving like a 6 electron system. 6 electron thermal cyclization is a disrotatory cyclization. So the hydrogen in this position and the hydrogen in this position end up cis with respect to each other in forming this 4-2-0 bicyclic system of this kind. So you have now done 2 pericyclic steps. One is an 8 electron cyclization, which is a thermal conrotatory process. The other one is a 6 electron cyclization, which is a thermal disrotatory process, resulting in the formation of this molecule. Now this molecule can undergo Diels-Alder reaction with the dimethylacetylene dicarboxylate. So essentially that is a process that is going to take place. This is an endoselective dimethylacetylene dicarboxylate endo approach to produce this particular molecule. In other words, compared to these two hydrogens which are in this pointing in this direction, the dimethylacetylene dicarboxylate should come from the side of these two hydrogen rather from the side opposite to this two hydrogen, which will be hindered by this bridge, for example. So the least hindered approach is the endo approach in this particular case, resulting in the formation of this particular product. This is a 4pi-2pi cycloaddition reaction, so it's a suprafacial cycloaddition reaction is what is taking place. Now this is a strained molecule. This can undergo retro Diels-Alder reaction. Essentially one of the molecule is already produced. This is a dimethylacetylene, like this is a dimethyl phthalate is what is formed here. Phthalic acid ester, dimethyl ester of phthalic acid is produced here. That is one of the product here. If you can see here, this is one of the products. So we have already formed that particular product here. And this is a retro Diels-Alder reaction which is forming the cyclobutene derivative. Another trans dimethyl cyclobutene derivative is formed. Under the reaction condition, it will open up in a conrotatory fashion. It's a electrocyclic ring opening reaction under thermal condition to produce this. This is essentially same as this molecule. So these are the two final products that are indicated in the earlier slide. So the 5 pericyclic steps are also identified very clearly here. The first one is 8 electron cyclization, then followed by a 6 electron cyclization, a Diels-Alder reaction followed by a retro Diels-Alder reaction. Finally, a 4N cyclization is what is said. So when you take this molecule with dimethyl acetylene dicarboxylate and heat it strongly to 200 degrees or so for a prolonged period of time, these are the two thermodynamically stable products. This is an aromatic product, and this is of course a conjugated diene product. These are the two products that are formed. Perhaps the driving force is the formation of this aromatic product coming from the retro Diels-Alder reaction, which drives the overall reaction to the formation of these two products that are formed in this reaction. A very interesting molecule because it is a very challenging problem to identify each step with the pericyclic selection rule and so on. So I thought I should present this to you in this manner. Another interesting problem, you are generating a methyl group which is a chiral methyl group. There is one hydrogen, one deuterium and one tritium substituted on the methyl group, so that makes this methyl group a chiral methyl group. There are two pericyclic reactions involved in creating the chiral methyl group in the following molecule. Identify the steps and suggest a suitable mechanism for this reaction. If you look at this starting material, there are hydrogens in these positions which are allylic hydrogens. There are hydrogens, there are deuterium in this position which are sort of ether kind of a linkage is what is acetal kind of a linkage is what is given here to form. So the hydrogen from this position can be transferred onto this one to get this hydrogen. In the process you will do a 1,5 kind of a shift is what you are doing. In other words, you can think of an ene reaction which is a 3,4 type 1 ene reaction is what we are going to perform here. So take this allylic hydrogen, push it over here with a concomitant rearrangement of the diene units here to form the connectivity between this carbon and this carbon will essentially produce the 5-membered ring. So the first reaction essentially is to identify the ene component. The ene component is identified very clearly as the 3,4 type 1 ene reaction. So this is the ene component and this is the enophile component. The acetylene is the enophile component which is already tritium substituted. So the ene reaction is shown here. The hydrogen is shifted over here with the concomitant formation of the carbon-carbon bond and the reorganization of the pi bond into this system, resulting in the formation of the hydrogen deuterium substituted derivative, which is this particular derivative. Now all you need to do is shift this hydrogen deuterium over here. This should be a suprafacial process. Remember, this is a 1,5 hydrogen shift, so it is a suprafacial process is what is going to take place. Here is a deuterium transfer onto this position. If you consider this, actually this is a retro-ene reaction is what this product is. Retro-ene reaction is what you need to perform in order to do this deuterium transfer over here. I will show that very clearly. You can transfer the deuterium over here with the loss of the deuterated methyl formate as the molecule. In other words, if you do a ene reaction between these two, you will get this molecule. The deuterium transfer over here onto this carbon with the concomitant formation of a carbon-oxygen bond should give this. So the reverse reaction is the ene reaction. The forward reaction as it is shown is the retro-ene reaction is what is performed. So transfer of the deuterium onto the methylene, which has the hydrogen and tritium already, produces the chiral methyl group. It is not an inertioselective synthesis. It's an interesting way of making a chiral methyl group in a racemic form in this particular case. The hydrogen migration is intramolecular type 1 ene reaction. The deuterium migration is a retro-ene reaction. I hope you got the retro-ene properly in this particular instance. This is a retro forward direction. In the reverse direction, you can imagine this to be a ene reaction between methyl formate, deuterated methyl formate, and this particular ene component, which is having an allylic deuterium in this position, like this. Finally, we come to this problem, which is a mechanistic problem. Suggest a suitable mechanism for the following reaction. It involves two pericyclic steps. You can see here there is a formation of a 5-membered ring between this position and this position, or you can imagine there is a cyclization process that has taken place to give these two products. Now if you take this molecule, what is that one can readily identify? One can readily identify the allyl vinyl ether portion very clearly. So one can see here the red portion corresponds to the allyl vinyl ether. Allyl vinyl ether under thermal conditions would undergo thermal Claisen rearrangement. So therefore Claisen rearrangement is a possible reaction for this molecule. The arrow shows very clearly the mechanism for the thermally induced Claisen rearrangement that puts the CH2-CHO group in this position, resulting in the formation of this particular molecule. Now this is a molecule which has this is the same molecule I am flashing again. This molecule has the necessary structural features that can undergo the ene reaction. The ene reaction, the enophile can be this allylic hydrogen, so this could be the ene component and this could be the enophile component. Alternatively, this could be the ene component and this could be the enophile component. Essentially, you have to form a bond between this carbon and this carbon to make this fused bicyclic pentene system of this kind, two 5-membered rings being fused in a cis fashion with respect to these two positions. This hydrogen and this CH2CHO group are cis with respect to each other. So if the ene reaction is taking place by the blue hydrogen migrating onto this position with the formation of this one, then that would form essentially this particular product. The hydrogen has migrated to this position, the blue hydrogen. So this product would correspond to the ene reaction product arising from this as ene and this as the enophile. If you take the red hydrogen and migrate it to this position, that would correspond to the other product. Again, the formation of the carbon-carbon bond between these two carbon is necessary for that ene reaction also. So two simultaneous ene reactions from different positions as ene component and the enophile component essentially produces these two products. The cis stereochemistry is essentially dictated by the superficial migration of the hydrogen onto this position, resulting in the formation of the carbon-carbon bond here. So that makes these two positions cis configuration, and this substituent is trans with respect to this. So essentially one can explain using a transition state structure involving a 5-membered cyclic transition state in a superficial manner to produce these two components in the stereoselective manner that it is shown in this particular transformation. Very interesting way of bicyclic 5-membered fused bicyclic systems of this type using a simple open chain structure like this by a Claisen rearrangement followed by a couple of ene reactions. I hope a variety of problems that are discussed in this particular module will help you think carefully about the way to solve the pericyclic reaction problem. I hope the examples that are given are interesting to you. Thank you very much for your kind attention.